Install the actual software.
I did.
You got the reason. This is started to.
Oh, you got it then. I would.
That's for the other class.
Oh yeah, but this one too. But
I just got it. Do you know how to do this?
it's easy. Just do it once. You think harder for you find that.
So which country are you? So easy to find out. We can't hear anyone.
We have to crop.
Okay. Should I open my handout?
No, it's not really that. I should transfer the voice to here, but
Thank you.
Fire system.
Your laptop is getting
Just 20 days back.
can close this thing. I don't know what to do that. Just click it. I don't know what it does. And that's it.
This is the machine of
Yeah.
is the problem solved?
No, I don't know.
I think there is no sound,
Yeah,
No,
yeah.
there is sound.
but there is sound.
In the YouTube, if you that there is sound, but we can't hear it.
Yeah, I have some, but I should move this mouse. So,
Okay.
but the previous one has some cable, but here no.
Should we call someone from the technical department?
Yeah, I don't know.
Is it
Call by
VJ?
phone.
Oh, it's okay.
I think she can call with this one.
But which number? Rizan, maybe call from that phone.
Yeah, and the difference.
But you won't have sound like this because
Yeah, but she's the technical
Yeah,
assistant.
yeah. It's
because
like
it's
a
only
signature.
VJ. There's no sound.
Yeah, but it doesn't have any.
Number is 293 students.
No.
Yeah, they gave the link and I think everything is clear.
Do you know?
I haven't received this. I just received it today morning, so maybe you can check it.
Like the pre.
Can you see this? No, when you open the Viaja, you get it. We can't do it because you have to. Only the login ID can do. So if you are logged in Viaja, you can.
Bonjour, on le fait le 25 américain. Puis à fond, on voudrait avoir du son, mais maintenant, tout ce qu'on a, c'est un câble VGA. Pas d'autre câble pour le son. Je crois que c'est possible d'en avoir un.
It's like you have 4 weeks. So each week from one
Non,
university. This week, I guess it's from the University of Water.
Oui, ça, something under this
Like it says, how do you
It's like.
your master's is in university? Very
What?
No, it's not.
the master's is in
Non, en vrai,
and your PhD is in
c'est bon.
Maybe you can say.
learning. I am design
Ah, oui.
Ah,
with
okay.
Kristen.
You would call or
Okay, thank you. You should have some.
Hello, everyone.
It's from you.
Hello, Professor. We are still waiting. I believe we are waiting for University of Toronto, and then after that we should be able to start. May I ask everyone to mute their mic in the meantime until until it's needed to speak up, I suppose. Thank you. We will start as soon as Toronto joins.
And so they're waiting for us right now, I'm sure, to allow them. I was saying we start at 12, not 12:10. Yeah.
Hello, Al. Oh, I could hear PFT. Still setting up. For Laval or Toronto? Hello, Toronto. Are you?
Can't hear them in my.
No, Raouf, can you hear us?
I hear you now. So are you? Are you connected? Yeah. So we were waiting for you guys. Do you hear me, Al?
Java 710. Java 710.
There's two Java
Oh,
710s.
yeah. Hello?
Yes.
There's something.
Can you cut microphone?
That's Realtek. Change it to this guy. Java 710.
This one?
I think that's Toronto, right? Do you hear us, Al?
Yes, we can hear you now.
Okay. Great. So in this case we have everyone. Let me just confirm. So Toronto, you hear us well? Yes.
Yes.
Okay. ETS, you there?
Yeah, we are.
Okay. Laval. Laval. Hello, Laval.
Hello, we are connected.
Okay, good. So we have
Thank you.
okay, perfect. So maybe then we should start. I believe there is. Okay, so yeah. So if you're not speaking right now, please mute your mic so we can just proceed. So today let me welcome everyone to the Network Softwarization course on technologies and enablers. In particular, those who are attending this class but haven't really attended the other course, the companion course on Network Softwarization's foundations and principles. And if you are not attending the other course, let me ask you to consider these are really related course and complementary course. But again, this is optional. You don't have to, but this is an option for you to consider. So this other course is taking place on Fridays. But anyway, let me welcome you again to this one. So what we're going to do today, since we have new faces, at least here in Waterloo, I don't know about the other institutions, but there is probably some students who are attending this class for the first time. So what we're going to start by doing is an introduction to this course, actually to both courses, to the entire Network Softwarization Create program, and tell you about it, both the course components as well as other components of the course, including internships and whatnot. Do we have the slides here? So we're going to go through a set of slides that introduce the courses, and then after that we will start with the first class today, the tutorial on SDN. That will be also the topic for the first lab.
Share the screen and
share. Or maybe you can increase the size then. If you're not sharing the screen, maybe increase the size of the screen. Yeah. So do you see the screen, everyone?
Fine.
Yeah. You guys, everyone, see you see the screen here? We just shared the screen.
Yes.
Yes, from it, yeah.
Perfect. So again, so for those who are not familiar, so this is about the NSERC Create program. So NSERC is the Natural Science and Research and Engineering Research Foundation of Canada. It's a major federal government funding program that funds various programs, and one of them is known as Create. And Create is a program that is aimed at training highly qualified personnel in areas that are important for the nation. And so the network softwarization is under this program. So it was funded little over a year now, and so this is the second year of this program that lasts for 6 years. And this program, the Network Softwarization Create program, involves 4 universities that are listed here. We have ETS in Montreal, and we have 3 professors there, Professor Mohamed Shrayet, Professor Nguyen Kim, and Mohamed Faten. We have Professor Leslie Roche from University of Laval in Quebec City, and we have Alberto Leon Garcia and Hadi Benazet and Ali Tisgadam from University of Toronto, mainly Professor Alberto Leon Garcia, and myself here at the University of Waterloo. So the program encompasses all these 4 universities. And so what we're going to see through this brief set of slides is first maybe a quick introduction to what network softwarization is, what are the objectives of this program, what are the different elements composing this program, and the industry partnership, because this specific NSERC Create program on network softwarization falls under the industry stream. Okay, so that basically involves industry partners, who will be, for example, hosting, for example, internships, industry internship for those who would be interested in that. So what is network softwarization? So think of network softwarization is, it's an odd term because it doesn't really exist in the dictionary, but it's the idea of turning into software things that have been done in hardware, for the most part in existing telecommunication and computer networks. So it's actually a major trend in the industry that is pretty much revolutionizing how networks are designed, operated, and managed. And the main objective underlying this movement is basically to achieve better flexibility and programmability in how networks are designed and operated and management, facilitating their management with the ultimate goal to accelerate the introduction and deployment of new communication services faster than what the current state of affairs. So you can think of network softwarization as an umbrella term under which different important technologies are contributing, and some of the most important ones include the so-called software-defined networking, or SDN, but there is also network function virtualization, or NFV, but there's also cloud-based network architecture. So they all actually complement each other to provide this concept of network softwarization. So software-defined networking has as an objective to enable fast innovation by making the network programmable. Basically, there is one main concept underlying SDN, that is to decouple the data plane and the control plane and implement the control plane as a logically centralized component in software, making it very easy to program the control plane, and that basically decides how to, for example, how to forward packets in the data plane or the data path in the network. So basically, and the idea is to improve efficiency, responsiveness, and as well as cost effectiveness, because the traditional, say, routers and packet switches or network elements are expensive, and then basically by deploying this in the form of software on commodity hardware or cheap silicon, then basically that reduces capital expenses expenditures, but as well as operational expenditures in the way basically the network is operated and managed. So the second main concept in the network softwarization space is known as network function virtualization, and that's the idea here again of decoupling what used to be vertically integrated proprietary hardware middle boxes that are largely deployed in communication networks. And here we're talking about boxes that are dedicated to provide a particular function, not the basic routing or switching functions, but additional functions that are important to provide network services. You can think of, for example, firewalls for security or intrusion detection system and prevention systems, deep packet inspections, web optimizers, all the proxies that are deployed in the network to provide services are deployed as hardware middle boxes traditionally. And the idea of network function virtualization, again, is to replace this costly, difficult to upgrade and maintain hardware middle boxes with software appliances that are deployed in software on top of commodity hardware, typically in cloud data centers, okay? So again, so that's complement. So SDN, you can think of it as a way to flexibly and forward traffic in the network, and network function virtualization, you can think of it as providing value-added services on top of these basic networking functions. So another important component here of network softwarization is to basically to achieve the operation and management of these integrated SDN, NFV, and cloud architectures, and reduce the cost, the complexity, the management complexity, which is known to be the case, as well as reduce operational expenditures, notably in terms of energy efficiency. And that's also one very important component of what we foresee as part of this, at least this program. Okay, so what is clear today in the industry is that there is actually a major shift in, and that includes both telecommunication equipment manufacturers, you know, that build switches and routers and whatnot, as well as network operator, telecom operator, mobile network operators and whatnot. They're all moving towards this network softwarization by deploying SDN, embracing this concept, as well as NFV and whatnot. And many of these concepts actually have stemmed from a need of the telecommunication and computer networking industry. So the consequence of that is that there is a major need for expertise and computer scientists and engineers that have this particular background and expertise, and that's what this program intends to respond to by preparing highly qualified personnel that has this expertise. So what are the objectives specifically of this NetSoft Create program is to train, again, graduate engineers and computer scientists to help the Canadian industry and the industry worldwide to support this fundamental transformation of traditional telecommunication and computer networking environment into softwarized environment through deployments of SDN, NFV, and cloud-based management. And the idea here is to provide that in an open online education way. For example, the course on foundation and principle is provided in a flipped mode through video recordings and interactive sessions, and this course here is more dedicated to the hands-on aspect of network softwarization and practical training and software development in this space. So there are the target graduate students as part of the program are practice and research masters. Some of you are, but as well as PhDs, and several of you are in the PhD program. So I mentioned before that this falls under the industry stream of the NSERC Create program. So because of that, it is very important, and I think it's very relevant as well, that the students who wish to, in addition to taking the courses, also participate in industry internship. And there are actually requirements in order to be eligible for these industry internships. So there are four main elements to this program. The courses aspect, which, and there are two courses, I already mentioned that, on network softwarization. The course that takes place every Friday in the morning is dedicated to the principles and foundations of network softwarization. That includes SDN and FV and whatnot, but mostly the theory and the design of this type of networking techniques. And the second course, for which we are meeting today, that takes place every Monday in the afternoon, is dedicated to the technologies and enablers of network softwarization. So that's more the software skills, the hands-on, the practice aspect of, and that also covers basically the same topic as the NNFV, clouds and whatnot, and I'll tell you more about that in a minute. I think one very interesting aspect of this course, as you have already noticed it for those who are coming here for the first time, this course is taking place in 4 different universities at the same time and involves professors in these all 4 universities. And the advantage of that, obviously, is that each component of the course is actually taught by a leading researcher in that area. So basically, any of us can teach all these courses, all these components of the courses, or different topics in the courses. But actually, each topic, and there are 4 modules, each module is taught by a leading research expert in that area. So it's even more interesting from the perspective, because you will be exposed to more than one professor and the top researchers in the area. And another advantage of this course is the access to state-of-the-art test beds, and one of them is the Savvy test bed that was deployed by a number of the professors that are also involved in this program. That's a different project that basically deployed a Canada-wide test bed that includes cloud, SDN, and NFV, and so basically state-of-the-art test bed. For example, you will be exposed to, if you do your projects, or some of the labs will be supported by this nationwide test bed. So there is also, of course, a research component to that as part of the projects that are part of the courses. But beyond that, for example, if you are, you can do a research fellowship, and I mentioned about that in a minute, and that in the area of network softwarization. There are industry internships, I mentioned that as well. But in addition to that, since we want to provide well-rounded, high qualified personnel in this important area to the industry, we want also to provide an opportunity for those of you who are eligible and interested to also follow a training in professional skills. Okay, and we're talking here communication, collaboration, project management, and we're talking here about approximately a 9-day course that will cover those complementary skills that are useful for your future career. So this is the content of of these 2 courses. So this is the principle and foundation. So I'll go quickly on over this one. By the way, you all have access to the web pages of the courses, and all this information, or most of this information, is available there. There are 4 parts, or say 4 modules that compose each of the 2 courses. The first one that already started is dedicated to software-defined networking, and the second one is dedicated to cloud computing, but also network function virtualization, orchestration, and a number of emerging use cases such as the Internet of Things, 5th generation mobile networks, and smart cities. The third module is dedicated to sustainable management of clouds and networks, and the fourth module is will be focusing on software-defined optical wide area network, as well as software-defined radio access networks. So the first module is taught by the University of Waterloo. The second one is a combination of ETS and Toronto. And the third module will be supported by ETS. And the fourth part will be taught by Professor Leslie from University of Laval. That the organization or the structure of the technology and enablers course follows exactly the same thing. Okay, as we see here, we have 4 parts, but as opposed to the introducing the concepts, the theory of these different topics, here the focus is on labs and exercises and hands-on experience. Okay, so I may have not mentioned that the first course on the foundation and principle is offered in a flipped mode, where you get a video recording 1 week before the class, and then when you come to class, you basically, it's an interactive session where you can ask questions and answers and whatnot, and then followed by a quiz, which will be part of your course grade. Now, for the technology and enablers, instead of a flipped mode, as I mentioned before, you come here and then you go through a tutorial, basically a tutorial that takes you through, the practice, for example, of SDN and whatnot, and then after that, you will have a take-home exercise. Okay, that will have to be returned in a week or so after the class is offered. So more specifically in terms of the content of this particular course on technology and enablers, in the first part dedicated to software-defined networking, there will be three lectures or 3 classes during 3 weeks. The first one will look at the SDN data plane and will cover technologies such as Open vSwitch, Open Virtual Switch, that's a software switches, as well as Mininet, which is the de facto standard SDN emulation, network emulation platform, and that will be basically done in class here today. And you will have a take-home exercise on that. Then the second week will be looking at the control plane, and here we selected ONOS as the control technology that you will be exposed to it and have an exercise as well on that. And then the third week will be dedicated to a network virtualization, and here FlowVisor and OVX will be covered during the tutorial and the lab. Okay, for the second part, for cloud computing, OpenStack, a very important platform there for cloud resource management, will be covered in the first week, in this case, the 4th week of the entire course. Then programmable networks, you will be exposed to service orchestration and chaining as a lab. And then for network function virtualization, you will be exposed to federation, NFV federation tutorial and lab. And for use cases, you will be exposed to some IoT tutorial and lab. Then for data analytics, you will be exposed to cloud workload classification and prediction lab. So we're talking about data analytics. Okay, and in this context here, basically we collect a lot of data that is important for the operation and management of clouds and networks. And what we want to do is basically to extract knowledge from this monitoring data, and a way to do it is using, for example, data analytics techniques and prediction, as well as energy efficient and sustainable management will be covered as well. And here, a green ICT tutorial and lab will be provided. Finally, for the software-defined optical wide area network and radio access networks, you will be exposed to specific tutorials on 5G front haul network, OFDM, and flex grid, and dynamic allocation of bandwidth in the context of optical wireless or radio over optical, and from time to time, eventually we will have invited guest lectures from the industry that will provide you with some insight as to what is happening in the industry. Okay, I mentioned internship as one of the 4 components of this course. So there are 2 types of internships. There are so the internships here, basically the industry internship, the research, there are also research fellowships I mentioned before. But for the internship, there will be an application process. Actually, for both internships and research fellowship, there will be an application process, and in which, if you are eligible, in order to be eligible, you have to have successfully completed the 2 courses, the enablers and the foundational course. And once you do that, then you have to send your application to the professor of your choice, and then for the research part, you have to contact the professor in your university. And so the topics of the industry internship will be decided in conjunction with the industry partners. Okay, and we have a number of industry partners already lined up as part of this program. It is expected, obviously, that both research fellowships and industry internships are funded. Okay, so you receive pay for that, a research assistantship or industry internship funding, and they are typically in the of length 4 to 8 months. So 1 internship unit is 4 months. Typically, 2 internship units are 8 months, which is, I think, a good option here. I mentioned in addition to all of that, we have professional skills. So for the research fellowship, obviously here it means that you are doing your master thesis or your PhD research in the area of network softwarization. So that's where it makes sense for you to do a fellowship. So for professional skills, the goal is to do that in collaboration with MyTax, which is a federal government funding agency again here that basically supports scholarships for students and provide all kinds of soft skill courses. These are the different topics that eventually you will be exposed to: career professionalism, communication skills, presentation skills, teamwork, project management, entrepreneurship, and intellectual property are all some of the relevant topics here. So what are the prerequisites for funding core courses? You have to take these 2 courses. This is a requirement to do an internship and to follow the professional skills training. So I mentioned we have already a number of industry partners as part of this program. They include top-notch industry players in the area of networking and telecommunications, such as Ericsson, Telus, Bell Canada, and many others. All right, and with that, I think I have covered the overview of the course. And let me open the floor for questions, questions that you may have here or elsewhere in the partner institutions. Any questions?
Do you have a question?
Say again, anyone? Okay, seems like this has been very clear. We have no questions here, but if you have any questions.
Here, we have a question.
Is the MyTax workshop offered in the universities, or should we apply for that?
Oh, okay. So, yeah, this is in the works. It's to be determined. So, I think we have we will provide more information about that when it is available. Unless someone else, Al, do you have anything specific to add to say here?
We're trying to organize it so they're at the universities, but as you said, it's being organized.
Yes. Okay. So we will provide you with information whenever this becomes available through our various communication means. That would be through the websites or the Piazza discussion forum. Yeah.
Thank you.
Welcome. Any other question? Okay, hearing none. Again, if you have any questions later on, I think Piazza is a good way to maybe to post your questions, and hopefully someone will respond. So again, we have a number of tools through which we communicate, and the good thing is that we have Piazza that is basically accessed by students and professors across all 4 universities. So I think it's a good forum to exchange with students beyond the classroom here, but throughout all 4 classrooms, and eventually find partners for projects or whatnot. So I think that's something that you have already access to. So if we have no more questions about this course introduction, maybe we could start now with the class. So again, so every Monday when we meet, there will be a tutorial that will get you through the, get you through the process of learning about the tools and technologies and that are covered in that class, and followed by exercises. And here, so let's start here. Maybe. So let me just let's set up the slides here. So we're going to start with a brief introduction to to SDN, right?
Right.
Yes. So since basically some of you haven't really attended the other class and hence haven't been exposed to SDN yet, and since today we're going to cover some of the specific SDN technology, so we chose to to before we go through the hands-on, the lab, give you a brief introduction of software-defined network, the technology, so you know the concepts, and then after that, go through the lab. Yes. So Shihab will be providing that today.
All right. So I'll disconnect for 5 minutes and set up my laptop. We'll be back like after 5 minutes or so.
Anytime, do you have any questions? So let me introduce Thomas Lin. Thomas will be right. Labs and Professor Farr.
Hello? Can everyone hear us?
Yeah.
Yes.
Yeah.
Camera is fine. Okay, probably there is a background tab that's playing something. Maybe this one? Just close it. Okay, should be fine. Hello? Can everyone hear me?
Yes,
Yes.
Naran.
Yes, everywhere?
Yes.
Okay, all right. Yeah, we had a bit of an issue with connecting to the projector and everything. I think it should be good now. Okay, so let me open the slide and share the screen. So this is. Can I extend the display? This guy? Ah. Okay. That worked, right? Yeah. Okay. All right. Great. Okay. So let me drag the VM over there. You know what? Right. So you're using a VMware player? Okay. All right. That's good. Okay. Sure. Thank you. Can I have the transceiver for my mouse, please? Okay. Thanks a lot. All right, so I shared my screen. Can everyone see my screen?
Yes.
Yes? All right, great. Oh, saving the desktop. I'm just downloading the slide, saving on the desktop. Yeah. All right, thanks. It's not responding. Yeah, but it's kind of stuck here. Sorry, maybe let me just do that. It's okay. Um, okay. The full screen. Okay, so hello everyone. Sorry about the delay in starting the class. We had some technical difficulties here. So I'm Shihab. I'll be running you through the tutorial for this lab, and also the upcoming 2 more labs on SDN. The first one will be on OVS and Mininet, and the second one will be on the control plane, and the third one will be on network virtualization using SDN. So it's a bit hard to run a live lab session across distributed across 4 schools, but I'll put frequent checkpoints for questions in case someone has a question, people are stuck somewhere. Communication gets lost, and for all to address all these kind of issues. So the first part of the lab will be a quick introduction to SDN for those who haven't attended the first foundations session or not taking the foundations course, and then I'll start with the lab. So before I start, was everyone okay with setting up their VM? Hopefully everything was fine here in Waterloo and in the other schools as well. Was there any issue or anything? So we all have our VM with us?
Yes.
Yes. If the answer is yes, then while I'm going through the introductory part, fire up your VM so it's up and running, and we can start our lab right away after the introductory part. All right? Now, the username and password for the VM is already provided on the Piazza post, but again, in password, use that for credentials and also for the super user privilege inside the VM. Excuse me. So, first of all, this part of the lab is on software-defined networks, right? So before going into what software-defined network is, let's take a step back and take a look at what hardware-defined networks were, or the traditional, more the traditional networks were. So traditionally, like network control, which is the process of determining how the network devices will forward packets in the network, that process, which is called the network control, it was embedded inside the network hardware or the network routers. So the network routers would have hardware dedicated and specialized for packet forwarding. At the same time, some software component that is also responsible for determining how this network router will forward packets to other routers in the network. And this net control process in traditional network was what is called distributed. So since every router has a part of the control, there is some distributed protocol. There is some way for the routers to talk to each other. They coordinate between each other to figure out, okay, what is the exact network topology? What should be a path in the network if I want to send a packet to this particular destination? So this is the control process. And every router has a piece of software that implements part of the control process. And in a distributed way, they talk to each other and build a view of the network and figure out how to exactly route packets to the network. So the control, it was embedded inside the routers, inside the network devices. That's one property. And the other property is it was distributed. So there was a distributed protocol that was implemented inside the routers for network control. So these are the 2 key things that was present in traditional networks. Now, if we look at SDN, so that was a traditional network, right? Now, if we look at software-defined networks, or SDN, SDN changed these 2 key things from traditional network. So the one thing is previously control was inside, it was part of the device. Now SDN proposed to decouple, disaggregate this control from the devices. So separation of control and forwarding. That's one principle. And the other principle is previously control was decentralized, or there was a distributed algorithm for control, distributed algorithms and protocols for control. Now, wait, just a second. Is there any issue here? Is there any issue with UFT? So UFT, you cannot hear us?
Yeah.
We don't hear you as well.
We are connected. We can hear you.
Just to check, can any other person from other schools speak up to see if it's the same for everyone?
Yes, we
Just
can.
to check.
Laval can hear you.
Like
Okay,
ETS
that's
or
good.
Laval.
Yeah.
Can someone from there speak up?
Hello. Hello.
I see.
Hello, Waterloo.
Okay, wait. So oh,
Yes.
this was muted, not that. Yeah.
Okay.
No.
Okay. All right. Yeah. So, sorry about that. Yes. UFT. There's a question.
Yes.
Yes.
Okay, we were muted in two places, so it took us a while to figure out which one. Not all of the students in Toronto have their VMs set up, okay? So
Okay.
I wanted for you to pause so we can pair students that have the VMs so that they can follow your lecture, okay? So give us a couple of minutes so we can pair.
Okay. Then let's take like a 5-minute break or so, and then after that we start.
Okay, but don't disconnect or anything, just.
Okay. All right. Okay. So let's pause a little bit for UFT to sync up.
Okay, so you pair up with him. Who has VM over here? You have VM? Okay. Who has? Those that don't, go next to somebody. Right here. You guys okay? Okay. Okay, we're ready. Okay, now we can follow. Everybody okay now?
So UFT is setting up VM. Wanted to pause for 5 minutes. Okay. So we're just pausing 5 minutes for that. Just a second. So check this one. Let me speaker. What about this one?
Okay. Okay, we're ready. Thank you.
Yeah. This one is a separate system. This one. So you have 3 here, right? Which one?
Oh, this is the USB.
This is the USB, yes. So this one is
These two are both audio.
this to audio.
And this one. Not the
Hello? Yes, hello? Yeah. Sorry, we lost the audio for a bit.
We're okay here.
Okay, all right. Okay, so let me resume then. So yeah, I was talking about SDN, the two fundamental concepts of SDN. The one is the separation of control from the devices. The other one is the logically centralized control as opposed to distributed control. Which mean what exactly does that mean is now we have the network devices which are responsible for packet forwarding. That's the only task they can do. Now there is a separated or remote control plane which talks to these network devices through some protocol, through some southbound API, through some standardized, well, de facto standard protocol. Most popular one is these days OpenFlow. So these centralized control plane is implemented in software and deployed in one or more servers. It's a logically centralized control plane, which means it has a single system view, but in reality, it can be deployed on multiple servers for scalability, fault tolerance, and whatever reason. But it's separated from the network devices. So that's the key thing in SDN. So the centralized control plane implemented as a software, it can be thought about as like an analogous to an operating system in a machine, where the operating system abstracts the underlying low-level hardware and provides a nice API for application development. So this centralized control plane can be thought of as operating system to the network, where it abstracts the network devices and all low-level complexities and provides a higher-level API for easier network application development. For example, if someone wants to develop a custom routing protocol or a traffic engineering algorithm, that can be done and built using these APIs on top of this control plane without necessarily being concerned about too much low-level details about the network devices. So this is like another layer of abstraction over the devices. Now, that's the quick overview of SDN. What's the fundamental difference with traditional networks? Any questions before I proceed here in Waterloo? Other places? Other schools? Toronto, ETS, Laval? No questions? No? Okay, all right, yeah. Show me a thumbs up or something. Just so that I know things are going all right. Okay, so now moving forward, as I said, the first week of the lab will be focused on mostly on the data plane for SDN. The second week will be more on the control plane of SDN. And the third week, it's on network virtualization in SDN. So this can be seen as a use case or an example of how SDN can be leveraged for this orthogonal technology, network virtualization, which has existed on its own for a long time, to how SDN can facilitate network virtualization. And we'll look at example technologies under each of these category, how to use them. And at the end of the tutorial session, there will be a next lab exercise which will be released by the end of the day. Depending on the week, we'll have between a week to two to solve the problem and submit. Submission instructions and everything will be posted on Piazza. Now, if you recall, as we said before, SDN requires this separation between the control and data plane, right? Now, there has to be a protocol that facilitates this communication between these control plane, centralized control plane, and the network devices or forwarding devices. At the same time, the network forwarding devices, they should be built with certain fields that they can recognize in the packet. Certain actions they can perform on the packet to be compatible with working with this control plane. So OpenFlow is one protocol. So it is one protocol for this communication between network devices and the control plane. At the same time, it also specifies how a network forwarding device or a network switch should look like to be able to work with a controller that talks to the switch using OpenFlow. So in a sense, it's both a switch specification. At the same time, it's a protocol specification. It's a southbound protocol specification. The way network forwarding works in OpenFlow is that there is a OpenFlow compatible data path or network device which has a forwarding hardware implemented. And at the same time, there is an OpenFlow agent running on the network devices. So this is basically the local agent that talks to the remote controller, takes the commands and parses them, implements on the switches and stuff like that. So there are many OpenFlow compatible SDN switches or SDN forwarding devices out there. For example, there are manufacturers like NEC, PK8. They manufacture hardware switches. There are also software implementation of this reference architecture. For example, Open vSwitch or Open Virtual Switch, which we will see or go through in this lab tutorial. But again, since all of them are implemented following a same specification, whatever we see for Open vSwitch, most of it applies to other hardware OpenFlow switches as well. You can see the same perform the same operations on the hardware OpenFlow switches as well. Yes, there's a question in Waterloo. Yes, go ahead.
What is the nature of the southbound API call? Sort of protocol
Okay, so the question in Waterloo is, what is the nature of this southbound API call? Is it like a protocol implemented using TCP or UDP or something like that, or something implemented on top of HTTP? The answer is OpenFlow is implemented on top of TCP. So the switches, the OpenFlow switch, the OpenFlow agent, more specifically, the agent on the switch, it maintains a persistent TCP connection with the controller. The controller communicates with this OpenFlow agent through this persistent connection. And OpenFlow protocol, it's a binary protocol. So there are protocol messages that are defined, and those protocol messages are like serialized, deserialized at the endpoints. That's how it works. Does it answer the question? Okay. All right. So as I said before, OpenFlow is both switch specification and control plane to data plane communication protocol. Now, OpenFlow switch, if we try to simplify how an OpenFlow switch looks like, it looks more like this. So it matches the packets, the incoming packets on something. Based on the match, it performs some action on the packets and maintain some statistics about the packets. So that's like a very high-level description of how an OpenFlow switch looks like. Now, what do we mean by match?
Chiap?
Yes.
We do have question from ETS.
Okay, sorry, go ahead.
Yeah, what does make Open vSwitch more used compared with the other SDN switch?
So if I get the question correctly, so the question is, what is the specific use of Open vSwitch compared to a hardware switch?
No, comparing with other virtual switch, SDN switch.
Compared to all the other virtual SDN switches? You mean the other software implementation of SDN switches?
Yeah, I mean, Open vSwitch is more used comparing with the others. What does it make it more used? What is the feature that is...
So if I get the question correctly, what is the main use of Open vSwitch?
No, I mean, there are different SDN switches.
Okay.
And Open vSwitch is more used comparing with the others. If I'm right.
Yes, Open vSwitch is more popular compared with others, yes.
What does it make it more...
Okay. I think one major thing is the community around Open vSwitch. I think that made increase its popularity over time. So initially, when SDN, the initial idea of SDN was proposed, and Open vSwitch was the first reference implementation, showed that okay, it works. Even if we deploy it on a server, it works. And at the same time, the community kind of started growing around it. It was the more popular one compared to the other one. And the other thing is, very soon, it was actually integrated into Linux kernel. So if we get a Linux distribution these days, most Linux distributions, they come with Open vSwitch. So for deployment into data center networks, since Linux is being used there more compared to others, so it actually gained more popularity because it ships with it, right? So that would be another driving force. Does that answer your question?
Yeah, thank you.
Okay. All right. Excuse me. So to moving on. So as I was saying, OpenFlow switches can be abstracted as this match action counter in this particular format. So when I say match, what exactly does it mean? So if we look back to traditional routers or traditional switches, so traditional routers, for example, they can look at a packet's destination IP address or the prefix of a destination IP address and decide where to send the packet. Right? That's how traditional routing works. If we look at switches, layer 2 switches in traditional networks, they look at the destination MAC addresses or the layer 2 physical addresses to decide why to send the packet out. So, and this so this process can be thought of like matching against something. For example, in routers, we have a routing table that has destination IP prefixes, and we match against them. So in case of SDN, this concept of match is expanded to other fields in the switch as well, in the packet as well. We are not only limited to match the destination IP address or the destination MAC address, but we can match a packet against a lot of other fields as well. For example, we can look at the VLAN tag in a packet. We can have a table of possible matches where it states if the destination IP looks like this and the VLAN tag looks like this, then perform this action. So the concept of match is extended beyond just layer 3 or layer 2 entries to other fields in the packet as well. As a matter of fact, in the current OpenFlow specification, as far as I recall, there are 45 match fields that are defined, which means it is possible to match against 45 possible fields inside a packet to take a forwarding decision. So as you can see, compared to traditional layer 3 or layer 2 routing or switching, OpenFlow gives more flexibility in terms of how we can forward the packets in the network. And at the same time, not only we can forward based on exact values of packet field, we can also perform wildcard matching, which, for example, saying any destination that is destined for TCP port 80, any destination IP should be forwarded in this particular way, right? In this case, the destination IP is a wildcard address. We are putting a wildcard over there. It can be matched with anything. That's an example. Any questions from Waterloo? From other schools? You're good? Okay. So this is an example. This is an example of OpenFlow flow table entry. So as I said before, packets can be matched against some predefined matching rules, right? And so these matching rules, they are stored in a flow table entry, which is inside the data plane, or which is inside the OpenFlow switch, to be more specific. So an entry in this flow table, it contains rules defining how a packet will be matched. It contains actions which define what will happen if a packet matches this particular rule. And at the same time, it also contains some statistics, some counter, some information about how many packets have been matched, how many bytes, so on and so forth. Now, as I said before, a rule can consist of many fields from the packet. Like here, we are giving an example where it says, okay, which switch port a packet came from, what is the source MAC address, what is the destination MAC address, so on and so forth. And we can have wildcard fields indicated here by the asterisks. We can have exact values indicated by the specific values here. So this is a format, like an example of a rule. For the action part, there can be many actions that can be taken on a packet. For example, a packet can be forwarded, it can be dropped, it can be encapsulated inside following some specific encapsulation protocol, so on and so forth. So that is what is dictated by this action field. For example, this example here says, if we see a packet matching this particular signature, then our action is to forward it to port 4 of the switch. So this is a forwarding action. We could have dropped the packet. That would be a blocking action. These are examples. There are many actions defined under OpenFlow specification. Okay. Any questions so far? We're good here in Waterloo?
Yes, I have a question.
Okay, go ahead.
Is this the VLAN is only regarding to the Ethernet, or it is valid for any other frames like JPON or?
So VLAN is a protocol between layer 2 and layer 3, but again, it's considered as a layer 2 protocol. It's a layer 2 encapsulation technique to create multiple virtual local area networks in a single network.
Okay.
Does that answer your question?
I want to ask if there is some kind of pseudo encapsulated frames from the optical network, for instance, and the inside of this, the packet are the IP. So
I see.
Packet,
okay. So the question is there any protocol that also defines encapsulation from optical networks where IP packets will be encapsulated inside on optical transport or optical access network? Is the question correct?
Yes.
Okay, so the answer is the OpenFlow specification as of today, it is focused only on IP networks. It doesn't have any specific fields defined from the optical domain. But there are works going on for extending OpenFlow for optical networks as well. Those are ongoing works. For example, there is a working group on extending OpenFlow for optical transport networks. Those specific extensions, they can have their own specific protocol extensions, own specific encapsulations. But the core OpenFlow protocol, it was mostly targeted toward data center networks, and that's why it is mostly focused on IP networks. So as is, it doesn't have any specific thing for an optical network. Does that answer your question?
Yes. Another question is regarding to the flow table. Is this also contain the management data in this flow table?
So the question is, does the flow table contain any management data? The answer is no. The flow table is inside the forwarding devices, and its sole purpose is packet forwarding. It contains only data, only information that is required to forward a packet. It contains some statistics, but some bare bones statistics, not something very advanced.
So the communication between the OpenFlow switch and OpenFlow controller is based on IP routing table, isn't it?
The question is if the communication between an OpenFlow switch and the OpenFlow controller is based on IP routing table or not. The answer is yes. The OpenFlow controller communicates to the switch using a TCP protocol, TCP/IP protocol. Now that can be out of band or in band. Out of band meaning that there is a separate control network connecting the controller and the switches. It can be, it doesn't, well, again, at the same time, the out of band network doesn't have, can be SDN. There is no restriction on that. It works as the packet forwarding network as well, but it will use IP, yes, TCP IP for communication.
Okay, thank you.
Okay, all right. Any other questions?
Where is the stats in the OpenFlow store?
Can you please speak up louder? Cannot hear you properly.
Where is the stats control store? Are they stored in vision or the controller? Where are?
I'm sorry to interrupt you. Can you please come closer to the mic? I cannot hear you. Your voice, the volume is very low.
He's asking where the stats are stored, either in the controller or the switch, right? Yes. Where the stats?
Okay, so the question is. Okay, so the question is, where are these stats stored? Whether it's in the switch or in the controller. Did I get it right?
Yeah. Correct.
Yes. Okay. All right. So the flow table has some limited number of statistics. So each flow table entry, for example, contains counters stating how many packets matched this rule, how many bytes matched this rule, how many packets did not match this rule, and stuff like that. So this is some low-level statistics information which is contained inside the switch. There are more statistics. For example, there are statistics associated with the switch ports themselves. Now, in the control plane, it doesn't have to maintain any specific statistics, but it can. It can query the switches, query the forwarding devices, and get all these kind of statistics from the flow table entries, from the ports, and it can build its own view of what's happening in the network. For example, what is the utilization of all the links in the network? Is there any specific flow rule that is there for no reason? I mean, no bytes are being matched to this flow rule. For this kind of diagnosis information, it can collect all sorts of statistics in the network, but the counting part itself is taking place in the data plane. Does it answer your question?
Yeah.
Yes? Okay. All right.
I have a question.
Okay, go ahead.
How is the security between the controller and the switches defined? Like, can we configure individual switches from the controller using an application?
Okay, so the question is how is the security ensured between the controller and the switches? Did I get the question right?
Yeah.
Okay, all right. So the basic implementation does not really focus much on the security. The specification mandates that the controller talks to the switches using TCP over SSL, TCP SSL. So that's kind of the transport level security that we have. But on top of that, any additional security mechanism that's out of the scope of the specification itself. The specification does not really specify anything substantial to be implemented for a secure controller to switch communication. That's a topic of research. Again, if you look around, you'll see papers, research works that's working on this specific issue, securing the controller and switch communication channel. And also, there are also research that also show how this channel can be used as a covert attack channel for some malicious traffic. So there are all sorts of research in that particular area. But again, it's not really a part of the core open flow specification.
So anyone can modify the forward table in the switch?
Pardon me, so can you repeat the question?
So if the forward table is populated using the routing table in the controller, so any hacker can modify the forward table in the switch if there is no...
Yes, that is a potential security hole. Yes, yes. I mean, separating the control plane and centralizing it, of course, creates this vulnerability of this central point of failure, right? If the central point becomes compromised, definitely that compromises the whole network as well. But again, that's like another area of research that people are looking into as well. That was not really a part of core open flow specification. It's an activity of research.
My question is actually, is the switch only configured with respect to the controller, or any other person can modify the configuration of the switch?
So the question is, can any person modify the configuration of the switch?
Or is it only with respect to the controller routing table?
So there are two things here. So the configuration of the hardware itself and and programming the flow tables themselves. So the controller usually programs the flow tables, not really the configuration of the hardware. There is a separate protocol for doing that. That's called OFConfig. And also there are definitely CLIs for the devices that can be used to configure them. Configure as in like we can configure a switch saying that, okay, use this particular IP address and port for your control channel, right? That's like the configuration for the device itself. And when we talk about open flow and central control plane, we are mostly talking about modifying the forwarding rules in the network, which is termed as the programming the network itself. that's not really part of the device configuration. You see the difference here? So when you say like configure the devices, definitely there is a separate configuration interface for the devices. There is a separate protocol for that. You can look it up. It's called OFConfig for open flow configuration. And also at the same time, the devices themselves, they can be configured using their own command line interfaces as well. For that, either there's a need to have access to a serial console or get access to the device. Does that answer the question?
Yeah, thank you.
Okay, all right. Yes. So the question is possible to have both in-band and out-of-band control for the SDN switches, and which one is more prevalent these days? So the answer is there is not really any statistics regarding that available in terms of production deployment. So I don't have a direct answer to that question these days, but that depends on the organizational practice, how they want to deploy this thing. But not really any publicly available statistics about like which one is more used compared to others.
Seems like the network would be prone to like session jacking.
Mm-hmm. Okay, so the concern here is if we are doing in-band control and we're not really putting any explicit security mechanism here, so the network will become prone to many sorts of network attacks. So the answer is yes, that is true. And again, that's been an active area of research, and definitely you'll find a lot of work concerning this kind of security issues in SDN. Yes. Now, we have another question from Waterloo. So the question is, aren't we using SSL? The answer is, it's not a requirement. It's like a practice. There is no requirement in OpenFlow to use SSL. It just says, okay, the communication is over a persistent TCP connection. Now the practice is to use SSL. But if you look at some early controllers, they had just plain TCP communication between the controller and the switch. Then the question becomes, okay, if the certificates are compromised, if there is a man in the middle, there are lots of concerns. Again, many people have looked at these issues from different angles. There is no straightforward answer to that. Yes. But again, that can be compromised if you. I mean, it's based on a trusted party, right? If you compromise it, the idea is as long as the trusted party is not compromised, you're safe. So the same applies actually here as well. And for that, we don't really. Now, the organizations don't really have to always depend on trusted parties as we do in internet, right? They can have their own certificate. They can become their own certificate authority here because the communication is not like end-to-end communication between different parties here. So there can be there are lots of attack surfaces where things can go wrong. That's for sure. Yes. Yeah.
So I have a question.
Yes.
This seems like a rule-based decision making, right? So if there is any decision it has to take where it does not have the rule already, does it learn dynamically or does it have to be modified every time?
So the question is, it seems like there is a rule-based decision making. So there is some sort of rule in the switches, and we decide based on this rule. And so how does it work? Does the chemically over time using some process or what? Right?
That's right.
Okay, all right. So that is actually my next slide. I was going to explain. So if we move forward, let me explain how OpenFlow works here. Hopefully that will answer your question. So the way OpenFlow works, so far we have seen that, okay, there is OpenFlow data path, we have flow tables, we have rules installed, we match against the rules and take actions, correct? That's the data path. Now, how does everything fit together in a bigger picture? How does the controller and the switches, they work together? So the way it works is that, so first of all, we have this open flow switches. It has ingress ports and egress ports. We receive a packet over an ingress port. So the packet is matched against all the rules in the forwarding table, right? To see if we can find a matching rule and take that corresponding action or not. Now, if we don't find a matching rule in the forwarding table, what happens here is that the OpenFlow switch sends a message to the controller. It's called a packet in message. It's a specific message defined by OpenFlow specification. So it sends a packet in message to the OpenFlow controller. This message usually contains the header of the packet. Depending on the configuration, it can contain the full payload of the packet as well. So the OpenFlow controller gets this message, this packet in message, and it knows that, okay, there has been a packet in the switch, and the switch doesn't know what exactly to do with that because there is no matching forwarding rule installed in the switch. So the OpenFlow controller has a global view of the network. It knows the network topology. It knows the MAC addresses of the ports and the switches, the devices that are connected to them. So it uses this global view to compute the path in the network that this packet should take. So then after that, the OpenFlow controller creates another message. It asks the switch to install a flow rule using this flow mod message or flow modification message. This message contains the flow rule that the switch should install in order to be able to handle this particular packet. All right. So once the rule is installed, the controller tells the switch to start forwarding packets using this packet out message, saying that, okay, now you have the rule. You can now let the packet out and keep forwarding using this rule. So this is one part of the communication. So this is a high-level view of how this OpenFlow protocol works. It's more like a reactive protocol. The way it was specified initially is it's more like a reactive protocol where a switch receives a packet, doesn't know what to do with it, and then asks the controller using this packet-in message, hey, what should I do with it? Then the controller computes the route, installs this forwarding rule across on all the switches along the route, and for switch. For example, there is this flow stat message that the controller uses to ask the switch about statistics. Remember, like we saw these different stats associated with the flow table. So the controller can use this flow stat message to ask for statistics corresponding to a particular flow or maybe all flow in the flow table. The switch then replies using a stat reply message. So there are many other messages defined in the OpenFlow specification. So does that answer the question?
Yes, sir, it does.
And any other questions before I move forward? Yes, there is a question in Waterloo.
So if the switch doesn't know what to do,
right. Right. Yes. Exactly. Yes.
So has that caused any sort of?
So the question here is, since the switch is working in a reactive manner, right? It will ask the controller for a rule. Usually, what happens is the forwarding in the hardware in the data plane that takes place in nanoseconds. But when the switch communicates with the controller and gets back the rule, that probably take milliseconds to complete. Now, does it have any implication or not? So the answer is, first of all, this process happens only for the first packet, not for all the packets in the net, not for all the packets of that particular flow. So it's a one-time thing. So which means once the rule is installed in the switch, the subsequent packets, for them, the switch doesn't have to ask the controller for any information. So subsequent packets will be forwarded entirely in the hardware. So that's in the nanosecond. That will be performed in the nanosecond scale. Now, for the first packet, yes, it will incur a higher latency compared to the other packets in the and that is an inherent problem in SDN. Some workarounds to this issue is the controller can be implemented in a way to have some proactive forwarding rules installed in the switches for low latency traffic, for example, that it knows that there are particular classes of traffic that it needs to handle, and they should be always forwarded in with a very low latency. And for those cases, it can have proactive rules installed in the switches. So again, it's a matter of writing your controller or writing your control application for particular classes of flows, depending on how they should be treated. So there is flexibility in the control end as well, as to how you want to write your own controller or control algorithm. So there's that. But again, if you just look at the default scenario, definitely there is an issue with the first packet. But again, for the subsequent packets, it's fine. Does it answer your question? Okay, all right. Any other questions?
There's a question from UFT.
Okay, yeah, go ahead.
If we have some conflicts in the follow table, and some rules, and there are some conflicts in them, what will happen to the packet that match with these rules?
Okay, so the question from UFT is, if there are conflicting rules in the forwarding table, and what will happen if the packet matches with the conflicting rules? Did I get it right?
Yes.
Okay, all right. Excuse me. So the answer is, there are multiple ways of conflict resolution. One way is through this priority field. So open flow table entries also have an entry called a priority. And there can be different priority for different flow table entry, which means if there are two flow table entries which are conflicting with each other, the one with the higher priority will have effect over the other. So that's one way of doing that, to have priorities. And we know that, okay, there might be conflicts, but in case of conflict, we want this particular rule to prevail over the other. And that can be handled with priority. So that's one thing. The other approach is, there has been a lot of work in the area of network verification. And a significant body of work has been addressing this particular problem of ensuring conflict-free flow tables in SDN. For example, like there is this paper, I think a few years ago, called VeriFlow, that performs static analysis on the rules before they are installed in the network to make sure that there are no conflicts. If there is a conflicting rule, it will not be installed to begin with. And many of this research has been translated into products. So there are separate products that work with existing SDN controllers to make sure that the network is conflict-free. So there are no conflicting rules in the network. Because sometimes conflicting rules can lead to disasters, for example, routing loops or black holes in the network. So there are these separate applications, control plane applications for ensuring that thing. Does it answer your question?
Yes.
Okay, all right. Any more questions? No? Yes, there's a question in Waterloo. Yes.
There is some sort of intelligence in the switch, like if there is a similar flow after one flow, then at the same switch, then can switch make it seem like this flow is similar to the previous flow, and it makes an entry itself without asking the controller.
Okay, so the question is there any sort of intelligence inside the switch that if the switch says there are flow rules which are very similar, then it somehow consolidates those rules into some smaller set of rules without asking the controller? The answer is no. Sorry, was anyone saying anything? Okay, so the answer is no. By default, the switches do not have any intelligence. They just have this forwarding table, and it can be programmed by the controller. That's how OpenFlow specifies it. And does it answer your question? Okay, all right. So any more questions before moving forward? All right. So we have an idea of. Sorry. Does anyone have any question? Did I hear anything? Okay. No. All right. So now we have an idea of how OpenFlow works in general, right? We have data plane specification, protocol, we have the controller. We know about some of the messages between the control plane and the data plane. Now, as far as the lab is concerned, we will be focusing more on Open vSwitch or Open Virtual Switch. So what Open vSwitch is, it's a software implementation of an OpenFlow compatible switch. So OpenFlow specification has a specification for a switch with flow tables and whatnot. So Open vSwitch is the first software implementation of OpenFlow specification. So right now it ships with Linux machines. Most of the Linux distribution ships with Open vSwitch as well as Zen virtualization platform. They also ship with Open vSwitch. VMware, NSX, they have their own proprietary implementation, which is something similar to Open vSwitch. So it's pretty much distributed in many places in the server data center ecosystem. So what it has, the way it is organized is it has two major components. It has a kernel module, which resides inside Linux kernel space, which is actually the data path, and it has an user space module, which talks to the controller. So, sorry, oops. So the kernel module implements the forwarding for efficiency. It's in the kernel space. So any packet that's received by the network card, Open vSwitch can be, this kernel module can be configured with forwarding rules, and it will match packets on headers and forward it across other ports. So whenever there is a miss in the match table, which means there was not a forwarding matching rule found, the kernel module will actually talk to the user space process for Open vSwitch. And the user space process is responsible for talking to a controller, a remote controller, and getting the flow rules and installing the flow rules inside the kernel module. So that's how Open vSwitch works from a high level. So Open vSwitch comes with a few user space tools, for example, OVS, VSCTL or virtual switch control, and OVS OFCTL or OpenFlow control. So the virtual switch control tool is useful for manipulating, creating more instances of Open vSwitches, configuring them. OpenFlow control tool is useful for actually modifying the flow tables of the switches. But to work with all these things, so what we need is a way to create a network first, right? So that will be the goal of our lab. Create instances of Open vSwitches, create a network, and make it talk to a controller, modify the flow table, and see how things are working. But for that, we need a network first, and for that, we will be using Mininet. So Mininet is a network emulator. It is not definitely the standard, but it's the most popular one for emulating an SDN. It has a low resource footprint, so it can emulate an entire network on even like on a laptop or like a small device like a Raspberry Pi. But at the same time, it doesn't scale too much. For example, we cannot deploy a network with hundreds of switches, for instance, or hundreds of links. It doesn't work in that case. It's good for functional validation. So if we have an idea implementing a controller and want to validate if things are working properly or not, it's good for that. But it's not good for doing a scalable network emulation, where we want to play like a high volume of traffic and scale to many number of switches and whatnot. Now, so Mininet creates switches and hosts inside a physical machine, one physical machine. So the switches are created by using OVS as the underlying switching layer. So what Mininet does is it creates OVS bridges. So bridge, the term bridge refers to layer 2 devices that can forward based on MAC addresses. But in case of SDN, many of the traditional terms, they don't really mean what they used to mean before. For example, now when we create an OVS bridge, it is not limited to layer 2 forwarding anymore. It can forward based on all the 45 fields of OpenFlow. So we will be creating obvious bridges, which are the instances of switches that will be deployed on a single machine. And the hosts, they are processes that emulate hosts, and they are kept in a separate network namespace, which means the host can have their own network configuration, and that's isolated from each other. So those will be our switches and hosts that will be deployed by Mininet. So Mininet is right now installed in the VM. So we don't have to go through the installation process. But in case anyone wants to go to the installation process separately, the CLI command is given here. So let's go to the VM and try to instantiate Mininet and see what happens. Let's look at the network and all those things. So let me switch my screen to the VM. Excuse me. Okay, so wait. Okay, all right. I wasn't able to see the bottom of the screen. Okay, can I full screen? Yeah, the thing is I have to switch between the slide and this thing, so it's fine. I don't have to full screen, but let me make it bigger so everyone can see it. Okay. Okay. So can everyone see my screen? Is it large enough? Is the text large enough? Yes? Okay. All right. So Mininet is installed. So let's just start Mininet without any CLI option and see what happens. So we have to run Mininet every time as a super user. So we'll be using, like, whenever we instantiate Mininet, we'll be using sudo. So let's run Mininet by running sudo mn. Mn is the command to run Mininet. It is still... Okay, for some reason, let's see the bottom properly. What happened? Okay, probably there was another instance running on. So when we run Mininet without any CLI options, by just running sudo mn, we should see something like this. We should see it's creating a network, adding a controller, adding host, and whatnot. So by default, if we don't specify anything, it should create a network with one single switch and two hosts connected with the switch. Okay, so this is a very first step. Did everyone see that? Yes. Yes. Okay. All right. What?
We didn't get like that.
Sorry. Was there any issue somewhere?
No.
No. Okay. All right. So we'll try. We'll get familiar with Mininet by running a few commands first to see what has been deployed. So we'll go through these three first: nodes, net, and dump, to see what they do. So if we run nodes from the Mininet CLI, so as soon as you run Mininet, you should be inside Mininet command line interface. So there should be an interface with Mininet at the prompt. So when it has its own set of commands, we can run from here. So if we run nodes, it will show us the nodes in the network. Is there any problem somewhere? Okay. So when we run nodes, we should be able to see the nodes in the network. For example, here we have a few nodes. We have the switch, which is usually prefixed by S. For example, S1 is one node. We have two hosts. They are usually prefixed by H by default. And we have one controller. So when Mininet deploys a network, it deploys a very lightweight controller so that things work. So we have one controller deployed here as well, C0. Now, if we net from the CLI, it will show us connectivity information, the network links that are currently present in this emulated network, in this deployed emulated network. So, for example, here, what we can see is that first, we have this host H1, right? And it shows the interface of H1. H1 is 0. That's one interface of this host H1. It is connected with another interface in the network of another device. So that represents a network link, right? So a network link is essentially a link between two interfaces of two devices. So here, host 1 is actually connected to S1, interface eth1 of S1. Similarly, host 2, it has one interface. It is connected to another interface of this one switch in the network. And then we have this switch S1, and switch S1 has a local interface, a loopback interface, and two more links going out of its two interfaces, right, with each of the hosts. So this is a network information, the connectivity information in the network. It is shown by the group by the host. So for each node, what are its interfaces and which other interface does it connect to? Just a quick look. Yes, there's a question here in Waterloo. So C0 here represents the controller. So when Mininet deployed the network, it also started a reference, a very lightweight controller. So that's represented by C0. It's an SDN controller. Yes, when I say controller, I refer to SDN controller. Yeah, yeah. All right. So after that, if we execute dump from here, it actually prints a whole bunch of information about the whole deployment. So for example, if we look at the, okay, let me highlight a row here. Maybe it's easier. So, for examle, as I said before, the Mininet hosts, the hosts we are deploying, they're essentially processes. They're processes inside confined network. Yes, sorry. Is there any question anywhere? No? Everyone is good? Okay. Sorry, I heard something. Thought there was a question. So, as I said before, when Mininet deploys the hosts, they are not like full-fledged hosts. They are essentially processes running inside a network namespace. So it also shows the process ID that is associated with each of the hosts. So any operation we can perform on Linux processes, it can also be performed on the specific Mininet host, for example. Say we want to use Linux cgroup to limit the CPU utilization of a process. Since we have the PID, we can actually do that manually through a separate interface through Linux CLI. Just giving an example. Although Mininet has that functionality built in, but if you want to do separately, we can do that as well. Similarly, for the other host, again, we can see its interfaces and the corresponding IP address assigned to the interfaces, and also the process ID that is representing that host. For the switch, so for the switch, again, the switch interfaces doesn't have any IP addresses, so that's why we are seeing none after the name of the interface name of the switch. So dump essentially shows more information about the entities in the network. So these are some basic commands to see what has been deployed, what are the different basic configuration parameters associated with them. I think there is another one, links. Oh, oops, maybe link. Okay, so no, it doesn't work. All right. So if we go back, so before I proceed, any questions about the basic things? Deploying a network very quickly, having a quick look at what has been deployed, the connectivity and whatnot. Any questions before I proceed? Yes, there is a question here in Waterloo. It doesn't show any information about the controller connectivity. The connectivity information is showed about the network. So the question here in Waterloo was, is the controller not yet connected to any switch or not? The answer is Mininet doesn't show any information about the control network, how the controller is connected. So that's why we didn't see anything, any particular information about the C0 here. It shows information about the network itself, the data plane itself.
I have a question. Are the hosts the switches over there?
Excuse me, can you please repeat your question? I didn't hear it properly.
Are the hosts H1 and H2 the switches in the network?
So the question is, are the hosts connected directly to the switches in the network?
No, what are the hosts? Are they the devices or the switches?
Sorry, can you please repeat your question? I think part of the your voice got cut off.
She's saying, are the hosts are the same as switches?
Oh, the host. The question is, are the hosts same as the switches?
Yeah.
Okay, so the answer is no. The hosts are not the same as the switches. So the hosts are more like, say, you have an endpoint connected to a network, right? For example, you have your laptop connected to a network. So your laptop is the host, and the switch is the forwarding element that forwards packets within the network. For example, if you think about the wireless access point, you can think about that like a switch that forwards packets in the network. So the emulated hosts in Mininet are more like the laptops or the smartphones, the end systems. Yes, and the switches, they are the network devices that perform the actual forwarding. So the hosts, they do not perform any forwarding here. Does it answer your question?
Yeah, and the switch, doesn't it have like the local IP address in the network? Because it shows none over there.
So the question is, does the switch have any local IP address in the network? So the answer is no. The switch do not have a local IP address in the network. So IP address in this case is assigned, so they can be uniquely identified. Now for switches, switches usually have a separate ID called a data path ID that is used to identify each switch by the controller. That's a separate identification from the IP addresses. So they're not the same. So the switches are identified differently than hosts.
Yeah, thank you.
Any other question?
Yes. In the command of dump, why the local host IP addresses of the switch is the same as the controller?
So the question is, in the command dump, why the local IP address of excuse me. So the question is, why the local IP address of the switch is same as the local IP address of the controller, right? Yes. Correct?
Yes.
So the local IP address here corresponds to the loopback IP address for all of them. So this LO represents the loopback interface, which is essentially the interface that we have in our end systems that loops back packet back to the system. So the switch here, it is deployed on this machine, and the local IP address is actually the loopback interface. So whenever we try to access through that local port, which is essentially the loopback interface in the machine. Same for the controller. The controller is also on the same machine. It's on the local host, the same host as the other entities deployed here. Now it is possible to deploy the controller separately on a different machine and specify that IP address when we deploy the network using Mininet. In that case, we will see a different IP address here. Now, since we didn't specify anything now, trying to deploy everything out of the box, we deployed the controller on the same machine. So that's why we're seeing a local IP address here. Does it answer your question?
Yes, and another question is, how can I see the status of the Ethernet port? For instance, the whether it is on or off, whether it is up or linked or unlinked.
So the question is, how can you see the details of the Ethernet port?
Yes.
The answer is just wait a little bit. That's also part of the tutorial. We'll go through that. All right. It's in the next few slides. We'll go through that together. Okay, so there was a question in Waterloo, and yeah, go ahead. Okay, so the question is, are the Open vSwitch instances instantiated by Mininet, or were they already running on the VM when it was given? The answer is they are instantiated by Mininet. When we will exit Mininet, it will clean up those instances. There was one final question in Waterloo. I'll take it before proceeding. Yes. So the question is, what is the capacity of the switch? How many hosts can connect to the switch at the same time? Theoretically, there is no like a hard limit here. But the thing is, since we're deploying this thing on a VM, which is running on your laptop, right now we don't have much of a capacity. Probably if 10 hosts, if you connect just 10 hosts or more, things will be very slow. I think it's already not that fast. It's already quite slow. It will become even more slower. So it depends on the capacity of your underlying hardware. It's as fast, as powerful as your hardware. So was there any more question from other schools? No? Okay. All right, so moving forward, excuse me. So, okay, so moving forward. So as I said before, so these hosts, each of them are processes, but again, they have their own network namespace, which means each of them actually have their separate network configuration, which is isolated from each other, and it is not visible from like outside of the process. Now, the question is, how do we see the network configuration of the host? How do we actually execute something in the host, right? Because the hosts are not really useful if you cannot really use them. We cannot really use them as if they are like real end systems connected to the network. The way we do it is Mininet allows us to run Linux commands inside the host. So what we do is we first type the name of the host, followed by the Linux command that we want to run. So let's see as an example. So for example, say we want to see the network configuration of the Ethernet interface for host 1. In an ideal case, what we would do is if host 1 was a standalone machine, we would just run this ifconfig command on host 1, and it will show us the information about the Ethernet interface. Now, here, what we want to do is we want to execute that inside host 1. So we tell Mininet, hey, okay, we want to execute a command inside host 1. So start with host 1, h1 here, and followed by the command. So as you can see now, when I run ifconfig with h1 as a prefix, it shows me the detailed information about the interfaces. So what is, for example, what is the IP address of this h1 h0 interface? Similarly, if you want to see the interface configuration for h2, it will show us the IP configuration of host 2 here. And as you can see, the IP addresses for host 2, right, it has a different IP address compared to host 1 here, which had a different IP address here, right? So they have, although they are deployed on the same machine, and not really deployed as virtual machines or containers, but deployed as processes, but they have distinct network configurations. Okay. Okay. Sorry about that. And we can execute other commands from here as well. For instance, say we want to ping host 2 from host 1. So from host 1, we launch the command ping to host 2. Right? So the way it is working is it executed a command inside host 1 and launched a ping to host 2. Now, Mininet internally resolves these names to IP addresses, so we don't really have to be worry about if there is a DNS server and whatnot to resolve the IP addresses. So Mininet internally does that. Now, one thing, if you notice from the results that was printed here, is that if you look at this time field here, which is the round trip time between the hosts, the first RTT is significantly more compared to the other RTTs. Correct? Can anyone tell me why? Any idea? Yes.
Maybe the forwarding table has the latency.
Okay, sorry, cannot. The voice got cut off. Can you please repeat?
Maybe the latency for the first packet transfer needs the query from the controller.
Okay, and someone from Waterloo was saying something. Mm-hmm. Right. Yes. So the same answer from Waterloo. Yes. So that's the reason. Because of the first packet, for the first packet, the switch actually has to query the controller for the route, right? For the forwarding entry. So that's why for the first one we have a longer round trip delay because it waited a little bit inside the switch. And for the subsequent ones, it matches the rule that is already inside the switch. So there is no additional delay for that. We have a question from Waterloo. Mm-hmm.
Why is it not saving the flow?
Okay, so the question here is, if we try the command again, the first one has again excessive delay. Why isn't it saving the flow? So the answer is, flow table is a limited resource. And when we talk about hardware switches, it is not only limited, it is also very expensive and very power consuming because it's implemented in this hardware. Since we have a limited resource, we cannot keep the flow entries forever there. Similar to a L1 CPU, where we don't really keep everything there forever, right? So the way it works for SDN switches is that each flow entry has a timeout parameter associated. For example, I think the default is 5 seconds. So if a flow entry is idle for 5 seconds, that's the default. So it is expired. It's evicted from the flow table. So that's why it's not there anymore. So, but if it is not idle, if it is like there are packets coming in, then it's not evicted. It will be there. And if you start a ping, terminate it, and start another one very soon, you'll not see this excessive delay for the packet. Any other questions?
I have a question.
Yes.
From the second set of packets, the timing is a little bit random. You're just using one host and one controller. So why is it like constant or particular pattern?
Excuse me. Sorry. The question is for the subsequent packets, the round trip time is not really constant. It is varying a little bit. And if it is in the same host, then why that is the case? Is that the question?
Yeah.
The answer is okay. The simplified answer is since even if it is on the same host, the latency you'll see depends on how the packets are being scheduled inside the network, right? When they are forwarded through the network, how they are scheduled. So in this case, there is only one interface, the local interface that is responsible for forwarding all the packets inside the host, as well as communicating outside of the virtual machine. Okay, so here the packet processing latency is very unpredictable. You will see unpredictable numbers here because there is no guarantee that there is a dedicated interface for just forwarding the packets between these emulated hosts. There is one interface for doing all the networking stuff. So depending on how the packets are scheduled inside this interface, that will reflect on the latency. So that's why we kind of have this unpredictable latency here. So that's the reason here. But usually, ideally, if you have separate hosts connected physically over a network without congestion, you would see predictable latency, more predictable latency over there. Does it answer your question?
Yeah, thank you.
No problem. Any more questions before I move forward? Okay. All right. So moving forward then. Sorry. Okay. So there are a few other. There are a few other tools that's available in Mininet for manipulating the host. For example, we can open a separate terminal to a host. Again, that's just for convenience. There are other tools to test to perform some diagnostic operation on the deployed network. Say we deployed a network with a controller. We want to see if everything is working or not, right? If there is connectivity in the network or not. There is this nice tool called ping all. So if we do a ping all, it will perform an all-to-all ping. Right? If you do a ping all, it will perform an all-to-all ping between all pair of hosts. And this is just in one way of checking if everything is working okay or not. If some pair of hosts is not able to talk to each other, probably there is some issue in the deployment that can be in the controller, maybe some of the links are not properly configured. But again, that's something else to look into before we can move forward. There is another tool called iPerf. So iPerf is a separate tool to measure bandwidth between a pair of hosts. Now, this can be deployed separately. Mininet also has a wrapper command around this iPerf tool. So when we run iPerf from Mininet CLI, it will just randomly pick two hosts and perform a bandwidth test in between them. So here, I think it performed a TCP bandwidth test between host 1 and host 2. Well, again, we have just 2 hosts here. We don't have many hosts. And shows that, okay, it found about 10 Gbps of throughput between this pair of hosts. Yes, there is a question in Waterloo. So the way it works is that it starts the iPerf server in one host and iPerf client in another host. The client just pushes packets, like MTU size packets to the server, and it measures the bandwidth at the server end. It is based completely here on the virtual connection. Yes, yes, yes. So host 1, for example, runs the server, right? It has this virtual interface connecting to this virtual switch that has another virtual interface connected to another host, right? So everything is virtual here. Yes, there is no physical host or switches deployed. No. Yes, right? Any other question? So these are diagnostic tools, iPerf and ping all, just to test connectivity and stuff like that.
We have a question from ETS.
Yes, yes, go ahead.
I just want to confirm that there are 2 bandwidths. I just want to confirm which is in egress and which is egress.
So the question is, so can you please repeat the question? I didn't get it.
I saw there are 2 results from this iPerf. And one is 9.11 gigabits per second. Another is 9.12 gigabits per second. What does those 2 figures mean?
Okay. So they're reported by the 2 ends. So there is actually a client end. The bandwidth is measured at the client end as well, and there is the receiving end. So these are the 2 ends, both ends.
So the first is the sending point, and the second is the receiving point.
That is something I need to look up at this point. I don't exactly remember the order right now, but yes, one of them is sending, one of them is receiving. Need to double check that.
Okay, thank you.
Okay. All right, so that's like the very default network we deployed. Just one switch, two hosts. So we didn't configure anything. So we didn't configure anything on the links, how the links will behave, or maybe on the topology of the network. So now let's terminate this network, get rid of this network, and deploy something which has some more configuration parameters associated with it. So the way we do it is quit. Mininet will stop and clean up everything. Okay, so if we go back to the lecture note, I think I put an example over there. So I put another example in the lecture note that deploys another network where we can specify specific network topology to deploy using these dash topo parameter. And we can also specify additional configuration parameters for the network links. Network links like bandwidth. What will be the bandwidth of the network link? Previously, when we deployed the network, we did not limit the bandwidth of the network link. But for a network experiment, we might want to deploy a network with specific capacities on the links. Similarly, a delay parameter on the network link. So this delay parameter will be emulated on the network links to emulate this kind of delay. So we saw that when we do a ping between two hosts, it was quite fast, except for the first packet, right? Because everything is in the same machine, although not predictable, but quite fast. But if you want to do a particular network experiment where we want to have some sort of delay on the links, we can specify that as well. So let's deploy this topology from here and see what we can do with that. Okay, so there is no. Okay, so I am running Mininet with topology type single. So there are a number of predefined topologies that comes with Mininet. So single is the same as the one we deployed before. There are more like, for example, there's a linear topology where it deploys a chain of switches. There is a tree topology where it deploys a tree of switches, like a root node, and then children and multiple levels, so on and so forth. So right now, let me deploy a simpler one. And then for the link, so the link type is TC. TC is a Linux subsystem for shaping traffic on links. TC stands for traffic control. So we deploy a link with Mininet, which is shaped by TC. For that, we specify bandwidth. By default, the unit is megabits per second. So here will be the links will have 10 megabit per second bandwidth. And the delay would be 5 millisecond. So we are deploying a very simple topology with 10 megabits per second capacity links, and that has a delay of 5 millisecond. So, all right. So, did it work for everyone? Here in Waterloo, it's fine for everyone. Okay. How about other places? Did it work properly? Work okay? Any questions? No? Okay, all right. So let me first run a ping and see what happens. So if I ping from H1 to H2, as you can see now, the round trip time is not a fraction of milliseconds anymore, correct? So here, definitely, the first one has longer round trip time because of the flow setup delay. But the subsequent one, they have a round trip time of roughly 20 milliseconds. One way it's 5 and 510 because we have a single switch and two hosts. So from one host to another one way is 10 milliseconds, two links, and coming back is another 10 milliseconds. So the round trip time, it should be around 20 milliseconds. So that's what we have here, roughly around 20 milliseconds. Not exactly 20 milliseconds, but something around 20 milliseconds. If we run iperf, And we should see a bandwidth which is roughly around 10 megabits per second, maybe a little bit more or less. Yes. So, for example, we don't see 9 Gbps bandwidth between the sender and receiver anymore. Instead, something around 10, 9.5, 11, something around that. So that's because we deployed the links in a way so that they can emulate this kind of bandwidth and delay. Any questions? From Waterloo? No questions? Other
Yes,
places?
there is a question from ETS.
Yes, go ahead.
I want to confirm that iPerm is run on the V switch.
You cannot run iPerf on vSwitch. iPerf is actually an end-to-end bandwidth measurement tool. So it runs on the end hosts.
So suppose if I have several switches, then this iPerf is to test through one end of the switch to the other end of the switch, another switch.
So if you have, so the question is, what if we have several switches and we want iPerf to pass from one end of a switch to another end of a switch? So the way iPerf works is that an iPerf server starts on one switch, and we start, not a switch, a host. So we deploy an iPerf server on one host, and we deploy an iPerf client on another host. Now, the hosts, definitely they are connected to some switch, and there is a switch network in between that carries the traffic, correct? So the goal of using iPerf is to test the end-to-end bandwidth that we have available between this pair of hosts, the pair of end hosts. So we deploy them on the end hosts. Now, this default one just randomly picks two hosts, but we'll see that later on when we use Mininet's Python API, we have more flexibility as to where we want to deploy the iPerf server, where we want to deploy the iPerf client. So we have more control over where in the network we can deploy the server and client. So this tool here is just for diagnostic purposes only, just to check, okay, if we have connectivity between this in the network or not, if the network carries traffic according to the specified bandwidth or not. This is just for demonstration. But as we will go further, there is more flexibility in deciding, okay, we want to deploy the server here, the client here. That's through the API. Does it answer your question?
Yes, thank you.
Okay. Any more questions?
Question from you, please.
Yes, go ahead.
You said something about the round trip time between host H1 and H2, which would be around 20 milliseconds. Does it relate to the delay that we specified before? I mean, the 5 millisecond delay that we specified before?
So if I get the question correctly, as I said before, the round trip delay between the hosts, they should be roughly around 20 milliseconds. And then what exactly is the 5 millisecond delay we specified before, correct? Did I get the question right?
I mean, how did you understand that the round trip time here would be around 20 milliseconds?
Oh, okay. So we set the delay for a link. So the question is, how do we understand from the specified delay on the links that the round trip delay would be around 20 milliseconds? So the answer is, so the 5 millisecond delay that we specify on the link is one way, right? So if we send a packet from one end to the other end, it would take roughly 5 milliseconds. Now there are two hosts here, correct? Two hosts connected to one single switch. So which means there are two links between the hosts. From host 1, we traverse a link to the switch. From the switch, traverse another link to host 2, H2. Which means one way the delay is 5 and 5, 10. So if we talk about round trip, which is going to the other host and coming back, that would be 10 and 10, 20. Does it answer your question?
Thank you very much.
Okay, all right. Any more questions? Yes, no?
Yeah,
Okay.
could you repeat the timing thing again?
Sorry, can you please repeat? Your voice got cut off.
Could you repeat the round trip time explanation again?
So the round trip time explanation is we have just one switch here with 2 links, and for each link we set the delay to 5 milliseconds, correct? So which means if we want to go from one host to the other host, we have to go through 2 links. So one way it's 5 and 5, 10 milliseconds. The other way coming back, there's another 10 milliseconds. So there's the round trip time going to another host and coming back. So that's why it's 20.
Yeah, okay, thank you.
Okay, all right. So then, so to move forward, go to the next slide. Excuse me. So Mininet also has a Python interpreter. So again, Mininet is written using Python. This shell we are seeing for Mininet is a Python shell, and it also acts as a Python interpreter. So these hosts and switches, they're essentially Python objects underneath, and we can use the Mininet shell to invoke a Python interpreter to invoke the methods of these entities, like for the switches and for the hosts. So just to show an example, let me go here. So the way we invoke the interpreter is there is this short command py, and after that we can execute a Python statement here. Say we want to see what are the methods available for h1. So h1 is a Python object which is representing a host as well, but underneath it's also implemented as a Python object. So we can actually see the attributes of the object through the CLI. So if we like as in Python, if we run like we call this function dir over an object, we can see the attributes of the object. So here we are seeing the attributes of this host object, and let me run something from here. I think, for example, we can see the IP address or something from here. Something like pi h1.ip. Yeah. So h1 has a method for showing the IP address, getting the IP address implemented in Python. So we can actually run it from the CLI here to invoke that particular method of h1. And we can do it for other methods as well, just to illustrate. That's one way to do that. So by invoking that, it prints the IP address here. And most likely it has a method for Mac. I forgot. Yes, it also has a method for printing the MAC address for the interfaces. So similarly, other objects like the switch, for example, it also has its own methods. We can print them, and we can also execute call those methods from this CLI. We won't be needing this thing as much when we want to actually using the when we want to use the Python API. We will write our own script by calling the APIs, but this is just showing another way of using it. Now, okay, so we deployed very simple topologies so far, right? Not many nodes or switches. As I said before, Mininet has this capability of deploying custom topologies. It has a set of built-in topologies that can be deployed from the CLI. So for example, here on this slide, there are a few examples of custom topologies. Let's run just one and see what happens. The remaining one you can practice. So let's start with a simple, okay. This doesn't copy from here. So let me quit this one. Okay. Say we want to deploy a network topology that has 3 switches which are connected linearly between each other, like a chain. So what we do is to do mn. We type topo. This time we give it a different name, linear. That's a built-in type for Mininet. And when we specify these different type for mininet, we can also specify additional parameters related to that particular topology. So here, we are deploying a linear topology. We can specify how many switches will be deployed in this linear topology. If we specify 5, it will deploy a network with 5 switches, each connected to a host. So as you can see here, when we deployed the network, it deployed 5 hosts. Each will be connected to a switch. It deployed 5 switches, and it also deployed 10 links. So 9 links, 5 links connecting the switches to the hosts, 4 links which are in between the switches, because it's a chain, it's a linear chain of switches. That's how it works. So that's another custom topology that we can quickly deploy from the CLI. Okay, everyone was able to do that. Now, if we do a ping just to check from H1 to H5, that's one end of the network to the other end of the network. Definitely here we don't bound on the round trip delay, so it's hard to tell. But when we deploy the network, if we specified a specific delay for the network links, it would be easier to see. When we ping between pair of hosts, we'd see different delays, all right, different round trip delays when ping executes. All right. Any question? Yes, there is a question in Waterloo. So Open vSwitch is not specific to any layer because it forwards based on many header fields in the packet, and that can range from layer 2 to layer 4, like many layer 2 to layer 4 protocols. So it's not. Open vSwitch. Theoretically, they can, but the way they work is they are not really assigned IP addresses. So the interfaces on Open vSwitches, they're not assigned any IP addresses because there is no need, right? Because unlike layer 3 routers, which are designed for separating between networks, each interface corresponds to a network. In case of Open vSwitch, you can configure it, but it's not designed in that way. It is not like putting any boundary between these networks, right? It can act as a forwarding layer for a single network. It can act as a forwarding layer between networks as well, right? It kind of, the boundary between the layers is a bit blurred here. So if you think about like the traditional way where the switches, they are like specific to a layer, either for a LAN segment, for a router network. But in case of Open vSwitch, it works, it can forward packets, like the packet forwarding boundary is kind of blurred here. But again, you can configure it in a way to have the same behavior as a traditional layer 3 router. No, in a standard SDN network, they are not used as a router. No, they are used as a forwarding device that can forward packet on many header fields. That's the idea. That's the flexibility that SDN brings. Any other questions?
Oh, I have one. What is this OVSK at the end of the command? What does it represent?
You're talking about the slide?
Yes. At the end of the command, you have OVSK. What does it represent?
Okay. All right. Yeah, I was coming to that. So what we have seen so far is we can deploy different types of network. We can specify different configuration parameters for the links. Now, by default, Mininet uses OVS to deploy these switches, correct? But we can also change that. We can also tell Mininet to deploy the switches using a different implementation of a software switch. So OVSK represents the OVS Open vSwitch kernel module, Open vSwitch kernel implementation. There is also an Open vSwitch forwarding module that is developed for user space. That can also be used to deploy a network using Mininet. OVSK is the default one these days. Previously, I think the default one was the user space one. So even if you don't specify OVSK, it will deploy these OVS bridges using the kernel module. But there is an option where the OVS bridges, they can be deployed using the user space implementation of OVS. There are other virtual switches. For example, there is Indigo virtual switch, which is also an SDN, software SDN switch implemented using OpenFlow specification and additional features that can be used with Mininet as well. And there are many other software switches that can be used with Mininet as well. So this is also another option that will be that is possible to specify in Mininet. Now, for the purpose of our lab, we don't need it as much because we'll not be changing the switch implementation. We'll be working with the default switch implementation. Okay, does it answer your question?
Yeah.
Okay, all right. So now we have a network, right? We have a network up and running. There is also a controller that is talking with the switches. And we can see that from the result of the ping, right? We are able to ping between hosts. Now the question is, how do we manipulate the flow table by ourselves? Definitely, there is the controller that manipulates the flow table. But at the same time, there is also a CLI tool available that we can use to manipulate the flow table. So the CLI tool essentially talks to the OpenFlow switches using OpenFlow protocol and ask it to modify the flow tables accordingly. So this CLI tool is called OVS OFCTL, or OpenFlow control, that can be used to add or remove flow table entries from the switches, show information about the switches, and so on. So let's have a look at some of the examples of using OFCTL. Okay, so for the sake of demonstration, let me deploy a smaller network where it's easier to understand things better. So let me just deploy the barebone network first. Okay, so I terminated the previous network, deployed the barebone network, and I'm just opening another terminal window. Oops. Where I will be running OFCTL commands. Okay. Okay. All right. Just trying to make it a little bit bigger. Okay, should be fine, I guess. Everyone can see that, right? Okay. So the first thing, the first command is to show basic information about our switches. So right now we have just one switch in our network because we deployed a very barebone network with one switch and 2 hosts. So we have this one switch in the network, and let's first see some barebone information about this switch. So the command to show that would be OVS OFCTL, and again we have to run it as a super user. Show, then the name of the switch. So everyone was able to do that and have this kind of information on their screen here in Waterloo and in other places as well. So deployed a very basic network and show information about the switch on the screen. I'll go through the information. Okay, so one thing to notice here is this DPID. So as I mentioned before, DPID is the ID assigned by OpenFlow protocol specification to identify the switches, the forwarding devices in the network. DPID stands for data path ID. So this data path ID for this switch is this big, I think it's a 48-bit or 128-bit, I forgot. We need to just count the bits. So DPID is an identifier identifying the switches. So that's one thing to notice here. The other things to notice here is the capabilities of the switches, of this particular switch. What kind of actions this particular switch can perform. So there is a specific OpenFlow message called OpenFlow feature request. So when I executed this command, the CLI actually sent this feature request message back to the switch to request, okay, what kind of capabilities do you have? And the switch replied with specific capabilities does it has. For example, the kind of action it can perform. It has this output action, which is the basic forwarding action. It has this action to change the VLAN ID, the VLAN tag identifier inside a packet. It has this option to set the network layer type of service field inside a packet. So each of these monikers, they represent a particular action. And the details of the action, they can be found in the OpenFlow specification. If you just go to open an OpenFlow specification, query with these names, you'll find the details as to what does this specific action mean. Same with the capabilities. And then it shows the information about the ports of the switches. So each port that we saw before in Mininet, identified by S1, ETH1 or S1, ETH2, they are also assigned identifiers like port number 1, port number 2. That's internal identifier to the switch itself. We can see the MAC address of the switch and speed of the port and information like that. So that's like the basic information about the switch, what the switch can do, how many ports does it have, the identifier of the ports. So those are the basic information about the switch. Any questions? Any questions elsewhere?
Can you hear me?
Yes, yes, go ahead.
I remember that you said that the switches do not have IP addresses, but here we can see that S1 has a local IP address. What is the difference between this one and the thing that you told us that there is no IP, especially assigned to switches in Mininet?
I'm sorry. Where are you seeing IP address here?
Below
is it under actions or capabilities?
No. When there is something written local S1, which is talking about the address of the switch. There is an IP address assigned to this switch, but as you told before, the switch shouldn't have IP address assigned to it.
So these are not IP addresses. These are MAC addresses.
Okay.
These are MAC addresses of those ports.
Okay.
Okay. All right.
Okay.
All right. Any other questions?
Excuse me.
Yes, go ahead.
What about the rules that the controller installs in the switch? Can you see them with this command?
Yes, that would be the next thing I will show. Okay. All right. So, is there any question about basic information of the switch? Otherwise, definitely, I'll proceed to the next thing.
Is the S1 Ethernet one the host address or the port address of that switch?
Excuse me. Sorry, your voice is getting cut off. Can you please repeat your question?
The S1 Ethernet one, you have a MAC address, right?
For S1 ETH1?
Yeah, so that is the MAC address of the port of that switch or the
Yes.
host?
That's the MAC address of the port of that switch.
Can we see the host MAC address with that command?
Can we see? Can you please repeat? Can we see what?
Host MAC address connected to the Ethernet one.
No, we cannot. So this command is only for the switches.
Okay.
So if you want to see anything about the host, that has to be through Mininet console. So this OVS OFCTL command, that's only for the switches, specifically for the switches.
Yeah, thank you.
Okay, all right.
Sorry, one question from OVS.
Yes.
Yes. Why we need to separate the Mininet and this OVS? I don't understand why we need to separate the functions.
Okay, all right. So the question is, why do we need to separate MiniNet and OVS OFCTL? So first of all, MiniNet in the network itself. MiniNet has some hooks into OVS OFCTL. It allows you to execute some of the commands, but not all of them. And so OVS OFCTL is separate. It's a separate tool in general for OVS, Open vSwitch. So I'm just isolating it here and to show what you can do with this. I mean, if you want to run these things from MiniNet console, some of them, MiniNet does support executing some of the OVS OFCTL commands.
So the topology needs to be executed first.
The topology needs to be executed first, yes. So we need a network first, right? Before we can do anything and see anything about or perform any operation on the switches, we need a network topology to be deployed, and MiniNet allows us to do that. So once we have this network topology, now we can access many things. We can see many things from MiniNet, as well as tools that were actually built for OVS to execute on the instances that has been created by MiniNet, and it will be the same. Okay, that does it answer your question?
Yes, thank you.
Okay, all right. There was a question in Waterloo. What do you mean? Can you please repeat your question? Okay.
In real implementation, in real world implementation of
Yes.
all these obvious features will be a part of STM control. Like you can do all this stuff from STM control.
Okay, so the question is, yeah, in a real implementation, all these things we are doing from CLI, it will be part of an SDN controller. The answer is yes, of course. Like the SDN controller allows you to do these things. At the same time, since we are now working without necessarily working with the controller, just with the data plane elements, there is also CLI tools that allows us to do the same thing. Yes. And that's also true for real implementation as well. So the SDN switches, they actually come with CLI interfaces, and I think I put a reference link on the slide. If you go there, so they have similar commands that can be executed, and the same effect with the same effect. Okay. All right. So we are running out of time today. That is 10 more minutes for the class. Okay, but okay, let's go through the slides and see how much we can cover. Now that was one thing to show basic information about the switches, right? And we can actually show the content of the flow table as well. So for example, there is this command that we can run with OFCTL, dump flows. That will actually show us the flow table. Now we don't have anything in the flow table because it's empty, because there was no traffic, and probably whatever rule was there is evicted. How about we do a ping? Let's go to the MiniNet window, start a ping from H1 to H2, and then run this dump flows command again. Wow, we have a lot of text here. So let me isolate part of the text so it's easier to see what's happening here. Maybe there are too many IRPs. Okay, let me isolate this one. So I highlighted a part of the text here. That is one entry in the flow table. There are many entries in the flow table. This is one entry. Just to show you a structure of a flow rule. How does the flow rule look like? So cookie is an identifier used to identify a specific entry in the flow table. It's usually set by the controller specific. Then we have this duration field showing okay, how long this table has been this entry has been in the flow table. Other than that, we can see a few counters. For example, the number of bytes, number of packets that has been matched. Remember, like I talked about an idle timeout and of the flow table entry. So in this case, it's 60 seconds. It shows the signature of the flow rule, for example, by showing the incoming port of the packet, the VLAN tag that should be matched, the MAC source, MAC destination, network source, network destination, all these fields. So it specifies an entry with all these fields. Excuse me. And to specify, okay, if we see a packet like this matching all these fields, then what should be the action? The action is at the very end. You see, like there is a field called action equal to output on 2, which means if we see a packet like this, the action would be to send the packet out on port number 2. So that's the structure of a flow rule. Now, depending on the controller implementation, the flow rule may look completely different. Because here the controller implementation is very basic, very simplified. It really doesn't optimize the flow rule. It basically puts all the header fields that it knows about and puts a value on it and installs a rule according to that. Depending on the control implementation, it might implement a flow table entry that has, for example, wildcard entries, or a flow table entry that matches a wider range of packets. So that's the structure of the flow table entry, just to give an idea how it looks like. And any questions on that? There's a question in Waterloo. It depends on the control implementation. So it depends how the controller sets it. Most likely, this simple controller just ignores the field and says the same value everywhere. But if you use a different controller, you might see different values for cookies. Any other question from any other place? From any other school? Any other question?
Cookie and duration over there?
So cookie is a field which is usually set by the controller to identify a flow entry later in the process. But in this particular case, the controller is a very simple controller. So it didn't really put distinct values on the cookie field. But a realistic controller would put here so that it can uniquely identify a flow table entry. And duration would be the duration this entry has been in the flow table. If you run this command again, you will see a different duration now.
Yeah, thank you.
Okay. Any other questions? Okay, so if there is no more questions, oh, sorry, go ahead. Okay, I thought there was someone who was asking a question. Okay, if there is no more question, then I will go to the next command. Sorry, did someone ask a question? I heard a voice. No? Okay, all good. Okay, so this quick exercise is for you to practice for later on. But again, this is not the lab exercise we talked about, take-home exercise we talked about. This is more for practice when we go through the slide for your own practice. So the next thing we'll try is so the next topic was Mininet with a remote controller. Now, for the sake of time, we'll quickly go to how do we manually add flows, because Mininet with a remote controller will be covered as part of the control plane lab exercise. So instead of going through this one, I'll go through this particular one. How do we manually add a flow rule inside a switch? So in this case, we already have a controller, right? That adds a flow rule into our switches, and it's a very simple controller. So what we'll do is we'll terminate this network, and then we will deploy another network with no controller. Okay, so The way to do that is when we deploy the network, we specify this option in the CLI, dash controller equal to none. So it deploys without a controller, and we can see that if we do nodes, there is no controller here. There is just a switch, and there are 2 hosts connected to the switch. As a result, if we do a ping from H1 to H2, the ping should not succeed. Right? Destination host unreachable, because there is no one in the network to set up a path now. What we will do is we will manually set up a path in the network, just to get familiar with this idea, how to set up a path inside this network manually using OVS OFCTL. Okay, so the way to do that is using this OVS OFCTL add flow, this particular action. So add flow action is used to add a flow table entry inside the switch. So in this case, in our case, we have just one switch S1, and we have just 2 hosts, host H1 and H2. To simplify things, what we will do is we'll add entries to make sure if H1 is sending something, it goes to H2, because there are just 2 things. If H2 is sending something, that goes to H1. All right. So again, we do OVS OFCTL add flow.
Excuse me?
Yes. Yes.
So Toronto, we have to leave now as the next class is about to come in. So we're going to disconnect. Yeah.
That is Toronto?
Yeah.
Okay, all right. So this part is, the lecture is being recorded. So you can actually go through this recorded part later on for this part of the lecture, all right? Sorry about the delay.
Thank you so much.
Okay, no problem. Yeah, and for the others, so the way we do it is, so we do it using this OVS OFCTL. There is a command for OVS OFCTL add flow. So after add flow, we specify we want to add this flow to. And after that, we specify the signature of the flow table entry. What should be the match and what is the action? Okay? Important things we need to mention. So that's the last thing we will be covering today. So probably should be taking 5 more minutes, if that's okay with everyone else. The remaining people like ETS, Laval.
Yeah.
Yeah, that's fine. Okay, all right. So first we specify the signature would be in port 1. Because we want to make sure the host 1 and host 2, they can communicate with each other, right? And previously we saw the switch has 2 ports, port number 1 and 2. So anything that is coming to 1, when we specify the signature as in port 1, it will match that. And then following that will be action to specify what we will do on the packet. So the action is to output on, oops, I think it is. So the action is output on 2. I think I got the syntax right. Okay, not right. Okay, so this is the action, then colon, then output on port 2. If we have a packet coming on port 1, our action is to output it on port 2. That's one rule we added. But did it change anything? It didn't change anything, because ping is a bidirectional communication, right? We send a ping packet and also expect something back. So we need to add, which creates the reverse path. So any packet 2, it should be go to port 1. And that should do the magic, yes. Now, as you can see now, up to this point, there was no path between the pair of hosts, right? The destination host was unreachable. As soon as we created this bidirectional path, now the hosts can talk to each other, because the ping packet is going in and also the. All right, so this is how we manually installed a rule inside the switch, and we can quickly have a look what is installed inside the switch. So this is the rule that we installed on the switch, and as you can is much more simplified than what was before, because not really very elegant way to write an incoming port and forwarding it to outgoing port. In reality, we would like to match on more fields, like for example, network IP, destination MAC, VLAN, VXLAN, and whatnot. So that's how we can actually add manual flow entries inside the data path to work with this kind of SDN switches. Now, the remaining part of the lecture is on the Python API part. I think for the interest of time, we'll skip the Python API part and stick to this. So by the end of today, I'll release the assignment or so. That will not include anything from the Python API. But again, for the Python API part, it's you can do it like a self-study process, go through it. I'll try to cover that a little bit before the beginning of next class as well, to go through the example, how it works and what the API calls we have, what can we be part of the take-home assignment. Only up to this part will be included. All right. Any questions for the material for today?
Can I ask a very brief question? What is the DAM standing for?
What is, pardon me, what is what?
What is the DAM? D-U-M-P?
Oh, what is dump? On Mininet console or here? On Mininet console here, dump?
Yes. Is there any abbreviation of some word?
No, that's not really abbreviation of anything. It's just like a log dump or trace dump stuff, something like that, but really an abbreviation.
Okay, thank you.
Okay, any more questions?
Is this employed in the traditional IP networks where the IP destination is identified by the network specific address? So is the controller IP address the network specific address there?
So the controller IP address, again, the controller creates a TCP connection, talks to the switches over TCP IP connection. So that's why the controller needs to have an IP address, which is like the we have. That is the way to identify the controller. Usually there is either a separate channel or there is a predefined rule in the existing network that can forward this control packets to the controller.
Okay, so any other device in the internet, if it needs to access the switch or the host, it should first access the controller by its IP address, right?
First of all, any other device in the internet should not allowed to access the switches, right? Usually the administrators, they are allowed to access the switches and whatnot. Controller, in most cases, I don't see it on a public IP address or public IP network. This is more like inside an administrator, like a more confined local network. So it will be having a local IP address.
I mean the host in the network, to access that, we need to access it through the controller, right?
So the host, so can you please elaborate your question a little bit more?
Because sometimes in the internet, instead of directly going to the host, you take the network specified host, right? And it goes till that point and then inside the network.
So for the hosts, they are completely unaware of the controller, the existence of the controller. The hosts do not see the controller at all. When the hosts want to communicate with other hosts, they know the address, the IP address and stuff for other hosts. It's the switches, the forwarding devices in the network that know that there is a controller. And whenever they need to set up a route, they ask the controller. But the endpoints, they are unaware that there is a controller.
Okay. Yeah, thank you.
Okay, all right. Okay, so if there are no more questions, then that's a wrap up for today. The assignment will be out by the end of today, sometime tonight, and hopefully we'll meet next week, same time. Okay. All right.
Okay, thank you.
Bye, everyone. Then. Yeah, bye-bye.
Bye, thank you.